Okay, we're gonna finish up calibration content in a video lecture. And to start, let's just review for a minute where we left off. We were talking about the idea of a calibration curve and preparing calibrations from standard solutions. So an example we could look at would be trying to find the concentration in this beaker of this green dye. So we make standard solutions with known green dye concentrations. We've carefully prepared them so we know that this is 12.5% green dye and this one's 100%. So if we just by eye make a look and see that this unknown solution looks like it's in between the concentration of 50 and 25%, we could make a guess and say, oh, we think it's maybe 35%, but right now it's just a guess. So what we need to do is measure some property that responds to the amount of dye, and absorbance is a good candidate for that if we want to quantitatively determine the concentration. So let's measure the absorbance spectrum for all of the standards. So here are the concentrations of the standards, and we pick a wavelength that's sensitive to changes in that concentration. So picking a wavelength around 400 makes sense because there's big changes with concentration at that wavelength. Picking a wavelength of 700 doesn't make sense because that doesn't respond to concentration. So we'll measure the absorbance for each of the standards, and we'll measure the absorbance for our unknown solution. And the next thing to do is to make a graph using that absorbance data at that maximum absorbance wavelength. So we'll plot the highest absorbance here on the graph right there. We'll plot the lowest absorbance here on the graph right there. And we won't plot the unknown absorbance. It doesn't go on the calibration curve. We'll use it later. We'll keep it for later. So we've got concentration of the dye on the x-axis and absorbance on the y-axis. And now we need an equation for that line in the slope-intercept form. So we need an equation that looks like y equals mx plus b. And there's our concentration of our absorbance of our unknown, so we need to keep that for later. We're not going to plot that on the x-axis, but if we were to, it would be here. We're going to exclude it for now from the fitting of the data, but just keep in mind that's where it would have shown up. So in Excel, there's a couple of ways to get your linearly squares best fit line. If you have a PC, you right-click on one of the points, and a pop-up box appears that says you want to add a trend line. If you have a Mac, I believe you push Control and then mouse click on it, or Command and then mouse click on it, and you'll get that same set of options. So we want to add a trend line, and we want it to be a linear trend line for this type of data. There's other types of trend lines you can fit depending on your application, but for most of what we'll do, we'll pick linear. We want to see the equation and we want the r-squared value, and we'll talk in a few minutes about what r-squared is. So now we have an equation for the line that says how sensitive our method is. The slope is the sensitivity. That's how much change in signal we get per change in dye concentration. So that's the sensitivity of our method, and this is the intercept. And we have a nice r-squared that shows our data is nicely correlated. Now if we add our unknown point back onto the graph, we can see that it's a pretty small concentration, somewhere between 0 and 10 micromolar, but we need an actual value. So let's plug in the actual absorbance value, which was 0.076, and solve for the concentration, which is x, in our equation for the line. So we're going to plug in our absorbance here that we measured and solve for x. So here's the absorbance of our unknown that we measured. That's from the graph. 0.076 was the peak absorbance here. Here's the slope of the line. Here's the concentration. That's what we want to solve for. And here's the intercept. So we just rearrange this algebraically to solve for the concentration. That's what this shows, and we see that we got 4.6 micromolar. That's what we got. Okay, so now we know how to solve for the concentration of an unknown using a calibration curve. There are some limitations we should talk about. One is that the response that we're measuring, whatever it is, it might be absorbance, it might be fluorescence, it might be electrochemical potential, whatever that response is that we're measuring might have a linear region where we can fit a line and get some nice data about the calibration. And it might have a region where the detector doesn't respond to concentration anymore. The detector might be saturated, or there might be some phenomena that's causing the detector to no longer give a response over a certain level. So we have to be careful when we make our calibration curve to make sure that we're in the linear range and not in this flat range. If we only measured between here where this line is and here, we might think we're in a linear range, but we won't be. It's not sensitive at all. This part, where the slope is quite steep, is a sensitive part. So we want to make sure we're in this region of the calibration curve. So some vocabulary is that this part is the linear range, where the response is linear. That's a sensible definition. Dynamic range is where there's any change at all in response. So we might still be seeing some small changes out here at this higher concentration, but that part isn't linear. It is a dynamic range, but it's not a linear range. So these are limitations to be aware of. And I promised we'd talk about correlation coefficient, and that's just a measure of how well the data can be fit with that best fit line. So in this case, most of the data lie on the best fit line. They lie directly on it. And if we measure the distance of the point from the best fit line, we'll get very small distances, and those distances are used to calculate the R-squared coefficient. So the correlation coefficient, or R-squared, should be very, very close to 1 if our data lie close to the line. If they lie a little bit farther away, we might still see a very nice linear fit to the data, but we can see that some of the points deviate above and some of the points deviate below, and if we take a ratio of that deviation, we won't be as close to 1 as we would like. So that is what this R-squared is showing. It's a little bit farther from 1. That ratio is not quite equal to 1. So we have a little bit worse correlation. It's still pretty good, but it's a little bit worse. Of course, the sloppier we are in the lab, or the worse our instrument is subject to variation. For example, if you have an instrument that changes widely with temperature, and your temperature changes during your experiment, you might get badly correlated data like this, where the correlation of standards is pretty far from the best fit line. So when we take a ratio of the data that fall above it and below it, it's not as close to 1 as we would like. It's getting farther and farther away. This is still showing a correlation, but our R-squared value got farther from 1, so that is a red signal that we're having some problems. Of course, if you have a look, data are linearly correlated as R-squared gets closer to 1. They're less correlated if it's farther from 1. And there'll always be, there's never a case where you'll have an R-squared greater than 1. The formula wouldn't ever produce that result. The worst case, of course, is if your data are completely uncorrelated. So you might get data that look like this, and you were expecting something linear, and you fit your R-squared, and R-squared in this case is very close to 0, it's very small. That tells you that these data are uncorrelated. There's something else going on. This might actually be a tremendously valuable insight, that your data are uncorrelated, and it might be telling you something important, but it's maybe not what you'd hope to find out. So a correlation coefficient is something you should always look at. If data are completely uncorrelated, your R-squared will be close to 0. Okay, here's a general rule of thumb. Your calibration data should be have a correlation coefficient greater than 0.9. Always aim for that, and if you're above 0.9, between 0.9 and 1, you're in a green light zone. Your data are fine. If your calibration data have a correlation coefficient less than 0.6, you cannot use it. You cannot use it to calibrate. It's unacceptably large correlation deficiencies. So you'll want to go back and revisit, is this really the right method? Is this really an analytical technique that's giving the response that you're expecting? So that gives you some important information as well. Okay, some other information that you can get from the calibration is something called a detection limit. This is the smallest quantity that's different from a blank. So this is not the smallest measurable concentration, it's just the smallest amount that's different from a blank where you have no analyte present at all. And if you want to calculate that, you get your linear least squares fit and find m. What's m? M is the slope. So remember, you fit your data to a line and you got a slope and an intercept. M is the slope. That's the sensitivity. And you also have an error in y. This is the amount of deviation you have in your signal, the error in y. So the minimum detectable concentration that's different from 0 is mathematically calculated as 3 times the error in y divided by the sensitivity, or the slope. The signal really must be 3 times larger than the noise to reliably be detected, and that's really what this equation is telling you. This is the noise in your signal, and you have to have a factor of 3 larger than that to get your detectable concentration. Now this is different from the lower limit of quantitation. So if you want to report an actual concentration for your method, your signal must be 10 times larger than the noise in this case. So the signal, it will be 10 times the error in your measurement in the y direction. So that's the error from your instrument divided by the sensitivity of your instrument, which is the slope from your best fit line. So let's see an example where this is used. This is a paper from the journal Analytical Chemistry that was published in 2011. And these authors were attempting to quantify testosterone using a microelectrode. This was for trying to detect athletes who were using performance-enhancing drugs. So from the abstract we see that using these microelectrodes, they developed an assay with a linear range between 0.01 and 10 nanograms per milliliter. So they're reporting where they had a linear response in their electrochemical system. Here's their limit of detection. So this is 3 times the noise with a detection time of 45 minutes. So it took 45 minutes to do the assay. So here's a problem you might see with limit of detection. Here is the limit of detection they quantified using their assay, and we want to know what the limit of quantitation is. So if an athlete in the Olympics is tested for testosterone and the lab measures 25 picograms per milliliter, should the athlete be banned from competition? So let's use our limit of detection information and compare it to this to decide whether we can ban the athlete. So the limit of detection formula is 3 times the error in y divided by the slope. So we can find S over M to find the limit of quantitation. So just dividing this by 3, we solve for the error in y over the sensitivity, S over the slope. And that's what this value is. This is the noise, essentially. The limit of quantitation then must be 10 times bigger than the noise. So 10 times 4.17 gives you 41.7 picograms per milliliter. This is the lowest concentration that we can report an actual number for. If it's lower than this, we can't report a numerical quantity for the amount of testosterone we've measured. So let's compare this to the amount that we measured for the athlete. The athlete had 25 picograms per milliliter testosterone. This is the limit that we have to have in order to report a number. So their concentration falls below the amount that we can perform. So we cannot ban the athlete from competition because we weren't able to quantify at a more sensitive level the concentration of testosterone. Okay, let's move on and talk about something called standard addition. This is another way to do calibrations when we have an analyte that's in a tricky matrix. So here's the idea. A tricky matrix would be something like a biological matrix like blood, or it could be a dirty matrix like industrial wastewater. It could be all kinds of different matrix components that we don't know. We might not even know exactly what's in this matrix, but there's an analyte within it that we're looking for, and we're hoping that the matrix doesn't produce a signal or doesn't suppress a signal, but we may not know this. So we're going to use something called standard addition to cope with a dirty matrix or a messy matrix. So here's some vocabulary. Matrix effects are chemical components in the sample that may influence the signal. It may enhance it or it may suppress it. And in the worst case, our real sample matrix may not even be well characterized. We may not know what's in it. So an example would be you want to measure a very low concentration of nickel, and if there's nitric acid present that might etch the glass in your volumetric flask, you might get a different signal than you would if you use nickel with a chloride counterion. So that's a real concern in atomic absorption. absorbance. Another example would be electrode fouling. So if you have a biological sample and you stick your electrode in it, components of that biological matrix might stick to your electrode surface and suppress the signal that you were expecting to see. So what can we do instead? Instead of using a standard solution that's prepared in pure water and comparing that to our analyte, which is in a dirty matrix, we need to prepare our standard in a matrix that's identical to our unknown. That's what standard addition is for. So here's how it works. Here's an example. We want to measure copper in seawater, which is a dirty matrix, using a standard that we've prepared in the lab. The standard is copper chloride in distilled water. So think to yourself whether or not distilled water would have the same matrix effects as seawater, and it's pretty unlikely. They're probably going to be different. So what are we going to do? We're going to run a calibration in the presence of the unknown and in the same matrix. So here's how it would work. We'll get 5 volumetric flasks, and in all 5 of these volumetric flasks, we're going to put 5 milliliters of our seawater sample. So every one of these has the same amount of seawater, 5 milliliters of seawater. In addition to the analyte, the copper that we're looking for in the seawater, there's all kinds of other chemical species that might enhance our signal, they might suppress the signal, but at least all of our samples have the same amount of that matrix now. In the first volumetric flask, we'll put no standard at all, and then we'll fill it up with pure water to the top. In our second flask, we're going to add 5 milliliters of a standard copper solution, and then we'll fill it up to the top. In this one, we'll add 10 milliliters of our standard and fill it up. Here's 15 milliliters of our standard, and then fill it up with water. And then we're going to add 20 milliliters of standard on top of this matrix and fill it up to the top. So all of these have the analyte in it, the analyte from the unknown, but only this one doesn't have any standard added to it. So we're going to record a signal. It could be anything. It could be electrochemical or spectroscopic. It could be whatever method we've chosen, and make a calibration curve. And here's what the calibration curve will look like. Without any added standard at all, we'll get a point here where this is the signal that's produced by our solutions, and this is the concentration that we've added, the concentration of added analyte. And your screen's cut off here, but this is the word analyte, based on final equal volumes. So we've prepared the same volume of everything, and this is the concentration that we added to the standard. Now in the first vial over here, we didn't add any standard. So we're going to have a point right here at 0 where we didn't add any standard, but we still have a signal that's due to the analyte that's present inherently in the matrix. And then we'll have a point here where we added 5 milliliters of standard, here where we added 10 milliliters of standard, here's our 15 milliliters, and there's our 20 milliliters of standard. And the question we ask is, if we hadn't added any analyte, we'd have a concentration of our unknown where we haven't added anything. We haven't added any standard. And we can get that concentration on the unknown by extrapolating this line all the way back to the x-intercept. And I'll show you some math equations to do that next, and then I'll show you the quick and dirty way to do this. So first we're going to see the painful way, and then we'll see the quick and dirty way. So here's our calibration curve, and what we've plotted is the intensity of our signal with our standard S plus our X, that's our unknown analyte, multiplied by a dilution factor, because we diluted all of our volumetric flasks. Remember, we added enough so they'd all have the same equal volume at the end. And here's X, which is our analyte that we've added. So that's the standard, the concentration of the standard in each one of those flasks times the dilution factor, because we diluted those volumetric flasks in the end. So this is the volume that we've added. So let's write some equations down, knowing what that we've got some dilution going on, and knowing that we're adding signal from standard. So an equation that's helpful to write down is that the intensity of whatever signal response we have that's due to our analyte X is going to be proportional to the concentration of our analyte in the initial sample. Okay, so this is concentration of our analyte that we're interested in. We've also measured the intensity of the standard plus the analyte together. So that's going to be proportional to the concentration of our unknown plus whatever standard that we added. And we can write these as a ratio, and this is one helpful equation to start with. So here's definitions of terms. This is our initial molarity of our analyte in the unknown. Here's the final molarity after we diluted it. Here's the concentration of our standard after we diluted it, and here's our signals either just due to the unknown or due to the unknown plus the standard together. Now, if we want to solve for the final concentration of X in terms of the initial in the matrix, we just use the dilution formula. Do you remember the dilution formula? M1V1 equals M2V2. That's what this is. So this is our final concentration is equal to the starting concentration times the dilution factor that we used. And that's for our unknown. And here's the concentration of the standard. And after we've diluted it, is equal to the starting standard concentration times the dilution factor. Okay, so what will we plot? We'll plot on our calibration term, our calibration curve, the intensity of our standard that we've added to the unknown times the dilution factor, and that's equal to the intensity of just the unknown. That's the y-intercept, the intensity just of the unknown, and then here are all of the X data points that we're going to put into our calibration curve. This is the intensity of just the unknown divided by the concentration of X. That's the thing we're really interested in ultimately. And this is the dilution factor, and this is the amount of standard that we add. All right, don't panic yet. We'll solve this in a way that makes sense. So here's our plot. The dilution factor times the standard that we added will be on the x-axis, and the intensity times the dilution factor will be on the y-axis. All right, what if you want to use a 2-point standard addition method? You can, and the math gets a little simpler, but this is a little less accurate. So this is the idea that you use only 2 volumetric flasks. One is your matrix that you dilute up to the mark with just pure water, and then you have another flask with your matrix plus some added standard that you dilute up to the mark with pure water. So you'll use a simpler set of equations where X initial is the concentration in just this blue region, but remember you dilute it, so you also have a final concentration that you diluted, and this flask has the standard that is added. So you measure the intensity in this flask and the intensity in this flask to get your ratio. And ultimately you can solve for the X initial just by rearranging this equation. So this is just a little bit of algebra to go from this equation up here to the one below, where we solve the initial concentration of X just in our blue seawater down here. Okay. Let's talk about how this is really used. You plot your signal that's rising in your flask due to both the matrix, your unknown analyte, and your standard. You plot your added standard down here times your dilution factor of the standard, and you fit it to a line. In this case, here's the equation for the line. Y equals mx plus b, where m is the slope and b is the intercept. And the intercept is essentially the signal that arises due to your analyte and your matrix together. So what will you do now? You'll extrapolate your line all the way back to the x-intercept, because solving for the x-intercept allows you to solve for the concentration of your unknown x that was in your flask. So how do we solve for the x-intercept? Well, what's the value of y at the x-intercept? The value of y is 0. We've gone clear down to 0. So let's rearrange our equation for the line, y equals mx plus b. Let's rearrange that to solve for x in the case that y equals 0. Well, in the case that y equals 0, we'll have x equals 0 minus the y-intercept divided by the slope. And when we do that, we'll have the concentration of our unknown. So in this specific example, we solve for the concentration x when y equals 0, and that's just going to be the y-intercept, the absolute value of the y-intercept divided by the slope. So pulling those numbers off of here, here's the y-intercept, we'll plug that in for b. Here's the slope, we'll plug that in for m. And the slope would have units of inverse molar or inverse concentration, whatever the concentration units are. And we would get a concentration of 2.891 molar. And that is what you see is the value about of the x-intercept as we've crossed the x-axis. So that means this is the concentration of your unknown x from a standard addition approach. If you want to get the error in this concentration, you'll just use the same standard deviation of x formula that we were using before for any linear least squares method, where you have the error in y divided by the slope. Here's the number of times you measured it. Here's the slope that you've measured. Here are the average y values from your calibration curve, and your values for x. Okay, so that's the end of standard addition, and there are several problems in your textbook that you need to practice, and the solutions for those are posted online. And we're going to move on to one final calibration approach called internal standards. So let's talk about the issue that comes up when you have a solution of your unknown and you measure it in some detector. It could be whatever detector you've chosen, and you put your vial of your unknown in and you measure a signal response. Then you take it out and put it again later and you measure the signal. You haven't changed your sample in any way. You're just taking it in the detector and out of the detector, and you're measuring it each time, and you're seeing some variation. It could be due to instrumental noise, or it could be due to environmental factors, but you're getting between run variation where you haven't changed your sample at all, but you're still seeing a large deviation in your signal response. And this is a really common problem that you see in spectroscopy and in chromatography. You see variation in the signal. So how can you cope with this variation if one time you measure it and it looks low and another time you measure it and it looks high? There's a trick you can use called internal standard, where you add something to the matrix. You add some internal standard to the matrix that's different from your analyte that you're interested in. So in this case, our analyte was myoglobin. That's what we were interested in. So we got to add something else that's different that we can measure at the same time that produces a shifted signal. So here's the signal from the internal standard. Here's the signal from myoglobin. And what we see is that when the myoglobin signal was low, like in the green curve, the internal standard signal was also low. And when it got to be higher, the blue curve, the internal standard signal was also higher. So this internal standard will help us measure variation that's due to the instrument or other environmental factors that's not due to real changes in the analyte that we're interested in. So that's what the purpose of an internal standard is. Okay, so what kind of math are we going to have to do? We're going to have to measure the analyte signal with a known concentration of just our analyte, and we're going to have to measure the analyte signal from our internal standard, a known concentration of internal standard. And once we do that, we can calculate what's called a response factor, or F, in this equation. And that helps us be able to make a ratio between our internal standard and our analyte under any conditions. So here's our standard analyte, here's our internal standard as well. So here's an example that we might see with an internal standard. Compound X is our analyte, and we measure a standard concentration of our analyte, 0.0837 molar, and we get a detection peak of 423 arbitrary units. We also measure our internal standard, and here's the concentration we prepared, and it gave a detection peak of this. So we can now calculate a response factor. So the first question is, what's the response factor for a calibration? And then the next one is, let's now prepare an unknown that we mix with an internal standard. Here's the concentration of the internal standard, here's the amount that we used, and here's the dilution that we used. Okay, so let's start with let's start with the response factor. We're going to use our response factor equation. Here's the signal produced by the analyte with the known analyte concentration, and the signal produced by the standard with the known standard concentration. So from our numbers, 423 was the signal response of our analyte. Here was the concentration of it. Here was the signal response of the standard and the concentration of it, and now we can just solve for F. It's just a little bit of algebra. We see a response factor that's a ratio between how our unknown responds and how our internal standard responds. Okay, so now we've got our response factor. We can start measuring the concentration in an unknown. So first we've got to consider that the standard was diluted. We took 10 milliliters of our standard and diluted it to 25. So we need the dilution equation. Let's start with that. M1V1 equals M2V2. So here's the concentration of standard we used. Here's the amount. And here's how much we diluted it to. So we can solve for the dilute concentration of our internal standard. And that's what it is. Now it produced a signal response of 582. And our concentration of our analyte produced a signal response of 553. So we need to find X. We need to find our analyte, our unknown analyte concentration. We know the signal response of that analyte. It was 553. We know the signal response of our internal standard. It was 582. We know from our previous calculation what the response factor is, and now we also know what the dilute internal standard concentration is. So we just have to rearrange and solve for X. And that's the concentration of the analyte in our unknown. So solving for X, we can get the concentration of our analyte in the unknown. Is this a real thing? Are there really examples where this is useful? And the answer is absolutely yes, particularly in spectroscopy. So here's an example from a paper in the literature where this authors were using Raman spectroscopy, and there's a lot of noise and a lot of variation in the signal from one run to the next. So their analyte response is what they were looking at. That's the BDMA, butyl dimethylamine. They were measuring how much BDMA was present inside these synthetic cells. So you can see initially there's no BDMA, and then the signal grows in at higher pH. But they needed an internal standard because there was so much between run variation. So they added perchlorate that was present all the time. In every sample, that peak here is the perchlorate, regardless of how the BDMA was changing. So even in cases where there's no BDMA, they have a perchlorate, and the perchlorate is constant. So you can see how much the signal changes in the perchlorate just from one run to the next, to the next, to the next, to the next, to the next. So you can see how essential it is to have that internal standard so you can account for that variation in a given run. So it's important to get some practice with these problems, and of course I can help you during office hours, and if you have questions, you're welcome to email.